This is Binomial Theorem, chapter 8 of class 11. See, in the previous classes, when 98 square we learned, what we did, we first changed 98 into 100 minus 2 because we know that dealing with 100 and a small number is easy, not very cumbersome. Similarly, the same logic goes for 999. So 1000 minus 1, that is we are going to deal with 1001. These are these numbers, these are small numbers, and these are numbers which can easily be handled just by increasing zeros. But this was square. We learned about cube. What if somebody says you 101 to the power 6? So you have to find the power of 6 of this number. You have to repetitive multiply 101, say 6 times, or even if you place it as make it as 100 plus 1, you have to find some or the other way to solve this. So in this chapter we are going to see this a plus b to the power n type of solutions, and we'll consider positive integer indices. The basis of binomial theorem is what we are going to see, and Blaise Pascal, he introduced this, and he introduced this with certain observation. If we observe for say a plus b to the power 0, anything to the power 0 is 1, anything to the power 1 is of course that number only. But square, we are aware that a plus b whole square, we have a formula a square plus b square plus 2ab. If we make cube of it, then it is going to be a cube plus b cube plus 3a square b plus 3ab square. But when we want to find out the fourth power, we can do one thing, that this we already know, a plus b whole cube, and this is a plus b. So let us take this and multiply it with ab, so it will come. Now, in all these computations, we have few things to observe. First thing is that the total number of terms on the right side, or the expansion, is one more than the left hand side, than the index. So if it is 3, the elements are going to be 4. The powers of first quantity, this a, is actually decreasing. A square, then a, then no a, no b and b square. So b is increasing, a is decreasing. Then the sum of the indices of a and b are same. For example, take this a to the power 4, b is not there, so take it b to the power 0. 4 plus 0 is 4. So everywhere the power will be 4. Take this a to the power 1 b cube. So 1 plus 3 is what? 4. So it will be 4 every time. So we observe an arrangement or a pattern like this. Okay, we have taken this 1 3 3 1 from here, 1 3 3 1. Similarly, 1 4 6 4 1. So if you observe this is called as a Pascal triangle. Pascal triangle, and you see, if you add these two numbers, you'll get this. If you add these two numbers, you're going to get this. You add these two numbers, you're going to get this. You add these two numbers, you're going to get this. So further, you can get the next one as 4 plus 1, make 1. 4 plus 1 is 5. 5 plus 6 is 10. 6 plus 10 is 10. And 4 plus 1 is 5. 1. So 1, 5, 10, 10, 5, 1. So now you have the coefficients of the next expansion also. This is your next expansion. So you have number 1, 5, 10, 10, 5, 1. This is called the Pascal's triangle, as we just saw. And if you take certain example like 2x plus 3y to the power 5, if you expand it, then this is 1, this is 5, this is 10, 10, 5, 1, as we observed in the fifth row. So fifth row, the power 5, the exponents are going to be like this. Now, the important thing is that in this case, the value of first say variable or first element is maximum when it is decreasing. While the first is nowhere, the second is nowhere, and it is increasing. This is quite a lengthy process if we increase it, say, to the power 10 or 11 or something like that. For that, let us have a proper generic solution. For that generic solution or general solution, we have NCR, that is factorial n by factorial r by factorial n minus r. NCR. We know this is the combination permutation stuff, so combination we can take. We know NC0 and NCN both are 1. So we have many ones here. All these are either NC0 or NCN. How about the middle one? These are, say, 5C0, 5C1, 2, 3, 4, 5. Okay. So now if we observe this pattern, we have, for say to the power 7, we have 7C0 till 7C1, 7C0 till 7C1. So 7C0, 7C1, 7C2, 7C3 until 7C7. And now a to the power 7, a to the power 6, then introduce b, because here b to the power 0, b to the power 1, b square, b. So b is increasing, a is decreasing. So this is the binomial theorem. Let us prove it using mathematical induction. So a plus b to the power n is this. Let us choose n is equal to 1. If n is equal to 1, a plus b to the power 1, it is giving a plus b. So this is true for 1. P1 is true. Let us assume it to be true for some k. So a plus b to the power k is, just place k here. Okay. Now a plus b to the power k plus 1. Let us see whether it is true for pk plus 1 or not if we assume it to be true for pk. So a plus b to the power k plus 1, here it gives you a plus b into a plus b to the power k. A plus b to the power k. What is this a plus b to the power k? This one. This we have already found out from here. This previous one. Okay. This, we are going to place this here. When we place it and when we actually multiply it, and we have to use these expression. K plus 1 C0 is 1. K plus C, KCR and KCR minus 1 is K plus 1 CR. And KCK or NCN is equal to 1, or NCN is equal to 1. K plus 1 C, K plus 1. If you multiply it, you will get this one, and this is nothing but K. This is true for K plus 1 also. K plus 1 also. Okay. So this is how we prove it using mathematical induction. How about x plus 2 to the power 6? X plus 2 to the power 6, 6C0, 6C1 till 6C6. Now x to the power 6, x to the power 5, x to the power 4, decreasing x and increasing 2. So no 2 square, 2 cube, 2 to the power 4 like this. So these are the numbers. And the observation here is that this notation, sigma notation, is actually giving you the value of a plus b to the power n, which is, the general term is nck, a to the power n minus k, b to the power k. This NCR, the coefficient of NCR, which are occurring or which are present in this binomial theorem, are known as the binomial coefficient. On the right hand side there are n plus 1 terms. Okay, and if you expand this, the sum of indices will always remain as n always. Let us take some special cases like a plus b to the power n. Now somebody says we want you to find out a minus b to the power n. So let us take a as x, b as minus y. So this is x minus y to the power n. And we'll do it exactly like a plus minus y, means a plus b to the power n. Just expand it. You'll see that all the alternate terms are going to be negative. So x minus y to the power n will be like this, and this, if you expand, alternate term will be negative. Otherwise, it will be exactly same as x plus 2y. If you take a as 1, b as x, so 1 plus x to the power n is going to give you this expression. Okay. 1 plus x to the power n is going to give you this expression. And if you place x equal to 2, 1 plus 1 is what? 2. 2 to the power n is nc0 plus nc1 till ncn. So if you only add the binomial terms with coefficients, it is going to give you 2 to the power n in this case. If you place b equal to minus x, that is 1 minus x to the power n, alternate terms are negative. So for x equal to 1, if you take x equal to 1 here, 1 minus 1 is 0. Or every alternative term will be negative, so these will cancel out. These are going to cancel out. So this is the first discussion on the binomial theorem. We'll be taking more of this. Thank you so much.